I don't like this. This is tedious. Well, eventually we will find we'll have a way to do this very well. But even before that, I can't even start to develop a theory because of this. This is just a mess, right? This dot, dot, dot stuff, and it's a mess. I would like to come up with better notation. Okay? In math, a lot of times you've got an idea. We've got an idea. We're using area. We're using areas of rectangles to approximate the area of the curve. You need a good idea, and then you need good notation. Okay? And then you put the two together, and you can get somewhere. Okay? So we've got a good idea. Now we need good notation to be able to extend this. All right. Just as an illustration, though, for how we go forward, okay, we increase the number of rectangles. Okay? Now, I think that when I say increase the number of rectangles, that's the most obvious way to see how this is happening. Okay? But actually what we are doing is, I want you to think of this as not increasing the number of rectangles, but decreasing the width of the rectangles. So the number of rectangles is becoming larger and larger. The width of the rectangles is becoming smaller and smaller. Okay? So I'd rather you think of it that way, but either way will kind of suffice for a little while. But you'll see where we need to be careful. Okay? So here we have this function, the natural log of x plus 1. I've graphed it for you. Okay? And I went ahead and I didn't do it. I told the computer compute R4, R8, R16. These are the right endpoint methods. You notice that? Okay. And these are the right endpoint methods. And each time I'm doubling the number of values, the number of rectangles. Okay. Something interesting to keep in mind here is that what's the width of this first rectangle? Yeah, 1 point something. We could actually find it, I think, right? Delta x is equal to b minus a over n, right? What's my b? 5 minus, what's my a? I think it's 0. Okay, that's all right. All over how many rectangles? 4. So I think we get 5/4 or 1.25 is the width of each of these intervals. Notice that 1.25 shows up here. It also shows up here as the right endpoint of the second interval. Okay? Because I am just adding more values into the partition here, notice that here I've got the values 1.25 and 2.5 and 3.75 and 5, and I forgot 0. Those are the values of the partition. This has those same values plus more, so we're going to call this a refinement of this, because we just added more values into the partition. Okay? So you could think of each one of these as a successive refinement, decreasing the width of each rectangle, which in turn, if I decrease the width, if delta x gets smaller, then for all things to remain the same, n has to get larger. Okay? And here you've got all the way up through R128. I know it's hard to read, folks, but it was the best I could do. So you can see that above you've got the estimated area, and then below that you've got the actual area. It's a little hard to read. Maybe you need your spectacles. But you're accurate to the 10th place. If you want to get more accurate, what do? Just add more rectangles, right? Okay. Then we could do the exact same thing with the left endpoint. How many rectangles do you see? How many rectangles do you see? I see 4. This is kind of a trick question, right? This rectangle right here has a width of 1.25, a base of 1.25, and a height of what? 0. So I know that people say, oh, I kind of dislike it in early math classes when they say apply common sense, because common sense really only gets you so far at math. If you guys had common sense, you wouldn't be here, actually. You'd be taking some other class, right? So we've already thrown that out the window. Anyway, I know that you can't really have a rectangle of 0 area, but what we're considering area here is simply a product of a base and a functional value. And functional values can be 0. So we are going to consider that area.